Here is the punctuated text. In a comment from teacher Carlos Honest of Durham College, I've spent my whole life constructing a specific perspective on the world, and now that thought is being addressed, I invite it since it is how we advance in science. James Webb is upsetting nearly everything in cosmology that has been acknowledged as obvious for as long as a century. Another ultra-profound picture affirms that we have made botches in cosmology. The telescope that should uncover the first stars of the universe is annihilating the earlier perspective and may introduce a new science. Not all analysts are terrified by the new data. Numerous researchers welcome the progressions since it has long been obvious that something was amiss with our past speculation. The irregularities in estimating the universe's expanding speed ought to have awakened scholastics a long time back. Rather than appropriately reading the signs, they stuck to obsolete ideas. The grandiose microwave foundation radiation, CMBR, is thought to be the most seasoned in the universe. The CMBR was framed roughly 380,000 years after the enormous detonation when the universe had cooled adequately for electrons and protons to frame stable hydrogen particles. Analysts allude to this change as reionization, and it made the universe penetrable to light. The CMBR was found in 1964 by American physicists Arno Penzias and Robert Wilson. While they were fostering another sort of receiving wire, they saw a consistent commotion coming from all directions overhead. This disclosure was long viewed as one of the most convincing bits of proof supporting the theory of the universe's origin. Penzias and Wilson shared the Nobel Prize and made history in astronomy. The CMB most likely gives a brief look at the youthful universe. Small temperature changes give huge data about the conditions in the universe not long after the huge explosion. Researchers utilized the CMB to gauge the universe's development rate, among other things. Edwin Hubble, a space expert, had previously made this calculation in the late 1920s. Hubble found that far-off worlds get away from us with speed relative to distance. Today, we refer to these estimations as the Hubble rule or the Hubble constant. Of course, Hubble didn't yet have the high-level estimation strategies that were utilized many years later. When the CMB was found, specialists recalculated the rate, and the new figure is significantly lower than Hubble's original gauge. Later researchers recalculated the rate utilizing type Ia supernovae as standard candles. Space experts approached such steady light that it very well could be used as a trustworthy estimating point. The error in deciding the universe's extension rate has existed since the 1990s. From that point forward, analysts have known, or rather thought, that something was off with the evaluation of the CMBR, the estimating techniques, or the idea of infinite development. The S8 pressure, or Hubble strain, refers to the contrast between the different estimated estimations of the universe's development rate. This has sweeping repercussions beyond a basic estimation difference. The numerous disclosures reveal significant insights into how we have previously perceived the universe. For quite a while, researchers were confused. Since its beginning, the James Webb Space Telescope has given researchers surprising outcomes, which may now illuminate the problem of the universe's development rate. Systems so old and mature that their starting point probably happened previously are totally in traditional science and astronomy. There could no longer be talk of estimation irregularities. Rather, scholastics are discussing the most difficult issue in contemporary cosmology. Not only could the universe's extension speed be mistaken, but the whole idea of extension or the Big Bang is being tested. Webb's photographs reveal evidence of a world that is incomprehensibly not the same as what we have long accepted. The pressure served as a first warning, and all specialists who continue to believe in obsolete theories now face a challenge. Do we actually know anything about the universe? Numerous researchers are now standing on the rubble of their life's work, gazing into space despondently and unable to appreciate how things are playing out. Given the ongoing scientific problem, we must ask ourselves, what do we genuinely know about the universe? To address this question, we must first understand how science works. Theoretical researchers utilize a complicated network of mathematical models, empirical data, and rational thinking to arrive at findings ranging from general to specific. Their skill depends on a combination of observed events, experimental data, and extensive theoretical examination. The name theory alone indicates that these are manifestations and ideas, not reality. We only have reasonable information, such as pictures from telescopes, sound waves, and radiation caught by radio telescopes, as well as the latest information from neutrino measuring systems or gravitational wave detectors. With the James Webb Space Telescope, we now have equipment that allows us to break down the earliest light into individual frequencies and analyze it in ways that were previously unimaginable. Webb can show us which elements were predominant in galaxies billions of years ago, how much mass was contained, and the number of stars. This shows that the telescope can modify a galaxy's structure and direction of travel. However, Webb may have flaws in some of its photographs. Due to massive accretion disks, the telescope can't tell us whether we are looking at galaxies or black holes that shine as brightly as galaxies. We must confront the fact that our science has long accepted too many potential outcomes as realities while disregarding alternative explanations. Research has long been certain that it is correct. The most recent findings from the James Webb Telescope provide vital signs for replacing old ideas with new insights, as has happened many times in science. Researchers are now anticipating new results. They are too odd, and it seems inconceivable for many analysts to come up with new interpretations right now. The new revelations are challenging the basis of current physics, which alarms many researchers. Today's physics courses are mostly based on Isaac Newton's discoveries in the 17th century. For hundreds of years, his principles of motion and gravity served as the foundation for our physical understanding of the real world, including the universe. Newton's rules explained the movements of objects under normal circumstances and worked well on Earth. In space, however, his ideas needed to be expanded, which Albert Einstein significantly achieved at the turn of the 20th century. His special theory of relativity, published in 1905, changed our perspective on space and time. Einstein showed that space and time are related to each other and depend on the movement of the observer. The general theory of relativity, published in 1915, expanded the concept by providing mathematical evidence of gravitational phenomena based on the curvature of spacetime caused by masses like stars or galaxies. Einstein's theories and ideas were generally strong, yet he approached his limits throughout his life. The scientist knew that his theories would never be adequate to describe the entire universe. He hoped to find the world's formula but did not succeed. Strangely, no other scientist has prevailed right up to the present day. Where's the error? Wouldn't it be interesting to know where the mistake is? Michio Kaku, a prominent astronomer from the US, stated in an interview that the individual who answers this challenge will undoubtedly win the Nobel Prize. Let us explore what facts researchers might have disregarded, where they may have confused events, and whether our telescopes are to blame. Dark matter and dark energy are among the most reasonable sources of the cosmic disaster. Our ongoing theories of the cosmos incorporate the possibility that dark matter and dark energy together account for around 95% of the universe. However, neither has ever been directly seen, thus their actual presence has never been established. Possibly they don't exist at all, and we must make sense of the universe's development and galaxy dynamics independently, or both have characteristics that we don't yet understand. One hypothesis now being examined is that the physical properties of the two dark components have evolved over time, which could imply that we are dealing with some form of intelligence. The next thing to be tested is gravity. This force, which supposedly causes attraction or shape in spacetime due to mass, has yet to be demonstrated. Einstein is fundamentally responsible for the concept of spacetime curvature, which has been repeatedly proven correct. However, we can't rule out the possibility that gravity has significantly different characteristics than previously thought, or that the gravitational force between objects is caused by a different mechanism. Some values, known as cosmological constants, have been established in modern cosmology and astronomy. Over the years, these values are largely reliable because they rarely change. Measurements have revealed that slight fluctuations in these constants bring new force into a variety of events. Without the presence of dark energy, it is also possible that our interpretations of the redshift of light are incorrect and that we have been measuring inaccurate distances within the universe and determining galaxy ages for a really long time. Perhaps our beliefs about the universe's original state were also wrong. We may have misread the cosmic microwave background radiation. It's also possible that the universe can't be traced back to a single origin point. This would suggest that the Big Bang Theory is wrong. Despite our refined technology, we can't rule out slight errors in the Webb telescope or other observational instruments. In the midst of the crisis, engineers and researchers agree that errors in instrumentation, data processing, and interpretation are always possible. The area of cosmology stands at a crossroads today, where the foundations laid over centuries are being challenged by groundbreaking observations and data from cutting-edge instruments like the James Webb Space Telescope, JWST. These challenges not only question established theories, but also open up avenues for completely new interpretations of the universe and its origins. One of the central pillars of modern cosmology is the concept of the Big Bang, which suggests that the universe began from an infinitely dense point and has been expanding since. This theory has been supported by various lines of evidence, including the cosmic microwave background radiation, CMB, the Hubble constant measurements, and the distribution of galaxies across the universe. The discovery of the CMB in 1964 was a turning point in cosmology, provided strong evidence that the universe had a hot, dense beginning. However, recent observations from the JWST have started to challenge some of the assumptions underlying the Big Bang theory. For instance, the detection of ancient galaxies that appear too mature for their age suggests that our understanding of the early universe may need revision. These observations imply that galaxies formed and evolved much faster than previously thought, which could point to new physics beyond the current models. Moreover, the discrepancies in the measurements of the universe's expansion rate, known as the Hubble tension, have become more pronounced with the new data. The Hubble tension refers to the conflict between the expansion rate calculated from observations of the early universe, using the CMB, and the rate measured from the local universe, using supernovae and other methods. This tension suggests that there might be unknown factors or components in the universe affecting its expansion. Dark matter and dark energy are two such components that have been hypothesized to explain various cosmic phenomena, including the universe's accelerated expansion and the formation of large-scale structures. Despite extensive indirect evidence, their true nature remains elusive. Some researchers now speculate that these components could have properties that change over time or might interact with ordinary matter and radiation in ways we don't yet understand. Additionally, the very nature of gravity, as described by Einstein's general theory of relativity, might need rethinking. While general relativity has been remarkably successful in explaining a wide range of phenomena, it might not be the complete picture. Alternative theories of gravity, such as modifications to general relativity or entirely new frameworks, are being explored to account for the observed anomalies. In summary, the field of cosmology is undergoing a paradigm shift, driven by new observations from the JWST and other advanced instruments. These findings are prompting scientists to reconsider established theories and explore new models that could better explain the complexities of the universe. While this period of uncertainty and reevaluation can be challenging, it also offers an exciting opportunity for breakthroughs that could fundamentally change our understanding of the cosmos.